I think I left the last section.
What's that?
I didn't realize there was a lecture.
Oh, okay. Yeah, I mentioned it at the beginning, but. Okay, someone help me out. So, what do we think about the answer to this question? Like, can we answer it, or like, what would we need to know to answer the question? Which group sleeps longer? Which sample sleeps longer? Yeah, Mairead. Okay, so we're making a guess, thinking it's group B. And how would you, so you made a guess, what went into your guess process?
Our guess is just because of the quartile range seems like it's maybe not as high as by A, but
Okay.
average it's closer together and higher up than A, which is has more standard.
Yeah, so first off, like we have much less variation in group B, but then also it may look like the interquartile range, like the box is shifted up slightly for group B. Maybe hard to tell. Anyone else? So if I were thinking about this question, first off, I think the question is underspecified. So if I were to say, well, let's say I think group B sleeps longer, but it turns out lots of people in group A sleep longer than everyone in group B. So I might need to ask a more specific question. I think implicitly when you're answering this question, nearly everyone here was thinking about the averages. Right, so like you're looking at this and you're comparing the middle points, so the medians if we're using the box. So maybe a better question is to ask which group sleeps longer on average. So that's something we can maybe answer better, because here the distributions overlap quite a bit, so we can't be clear that everyone sleeps more than everyone else in the other group. So let's compare them more precisely. You've all seen this. So this is how we define the sample mean. So this is like the average of our data. We just take all of the data points, we add them up, and then we divide them by n. So you're all familiar with that. This is our more compact notation using the summation symbol. So we're just summing over all of the i's. I like this notation. Some people don't, so it's up to you. But either way, we can actually just do this, and we've done a bit of this in Python already. But we can just take the sample, and then there's a built-in method to calculate the averages. So we're going to do a little bit of this a little later. Turns out group B has a slightly higher mean than group A, but by an imperceptible amount. So on average, group B sleeps a little bit longer. So no points for Mairead. Okay, so these are two groups, and this is just some of the conclusions here. We can also measure dispersion, so how spread out the data is. We talked a little bit about standard deviation, which is going to be the main tool we use. But I just want to walk you through a couple of quick ideas about the different ways that we could measure dispersion. The first one is range, so just the difference between largest and smallest. We've talked about this with the box plot. This is really simple and it's really nice, but the problem with range, the reason we don't use it more often is because it doesn't respond to movements that are not movements in the maximum or minimum. The only way we can move the range is by changing the maximum or minimum. And this is not a good property of measuring dispersion. So we generally don't use this one in our workhorse models. The other thing we could do is just measure the mean deviation. So we take every observation, every xi, and then we just subtract the average from it, just to get how far each data point is from the average. Do you know what this would sum to? take every observation, you subtract it from the mean, or you subtract the mean from it, and then you add up the average of all of those deviations. Yeah, Pete? 0. This comes out to be exactly 0. This has some nice properties to it, right? Like, what I'm trying to measure is just essentially how far away everything is from the middle. So it's a measure of how far things are from the middle, which captures this nice idea of dispersion, right? But the problem with this is it just adds up to 0. So the average distance from the average is just going to be 0. So this is not a good measure. So range doesn't work, mean deviation doesn't work. But I have something maybe slightly better. What if instead of adding everything up with positives and negatives, we just say we want to measure in absolute value how far everything is from the middle? This is definitely better. So it's all we're doing here is just saying how far is each observation from the middle, and then we just find the average of all of those. This is better. It measures like something about dispersion, how spread out the data is. If things are more spread out, this number goes up. If things are closer to the middle, then this number goes down. That's all very nice. So this has some nice properties. It's not 0, and it measures dispersion. But the problem is it's more complex. And it's, if you know anything about mathematics, which I think most people in this room do, this is not very nice mathematically. The plot of this is like a V, which has a point around 0. So it's not too complicated, but it also it doesn't let us take derivatives, which we're not going to do in this class. But that's the reason we don't like this one. Is for all the more sophisticated stuff we do, you can't take derivatives of this. Or at least derivatives are not so nice. So instead, we do something pretty close, where we can take a derivative. Here, instead of capturing how far away everything is from the average, we're going to do something that's pretty close to that same idea. So this is sort of a curved shape. It's like a U instead of a V, centered on the average. So when x gets really close to x bar, then we get very, very close to 0. And then as things get further away from the average, it starts sloping up. So I could have had some nice figures here. I don't have them in the slides. But essentially all we're doing is doing something very similar to measuring the average deviation from the mean. So this is nice. We're instead of having negatives, now everything is positive, just like with the absolute value. So that, we're measuring differences in both directions equally. The mean of this thing isn't 0. This is mathematically nice. The problem here, and you may have seen variance, the problem with variance is that the units are not informative. So this thing, we're squaring this, and squared units are just not very nice, right? So if I ask you, what does it mean to have, a variance of, $14 squared? Who knows? I don't know how to interpret that, right? The units being squared are just hard to interpret. So you all know what we do? We take the square root. So we take the square root of $14 squared. We can get something that's in just dollars, which is in the same units as everything else we think about. So this is what we call the standard deviation. We talked about it before. I think I've even defined it in the slides, but we're going to spend a lot of time with this. So I just wanted to talk you through sort of why, as an entire enterprise in science, we generally have agreed upon this as the most appropriate measure of variation. And it turns out these ideas are very fundamental. Okay, so a measure of dispersion, standard deviation is just a square square root of the average squared deviation from the mean. So we're saying a lot of things. The problem, this is very nice for a lot of reasons. Negatives are all turned into positives. So doesn't matter whether you're above or below the average, we're measuring the dispersion equally in both directions. The mean is not zero, so this thing will not turn into zero. And it's mathematically nice. And then the units are roughly equal to that original thing we defined, the average deviation from the mean. It's not exactly equal to it because just this, the square root of the sum of averages is not going to be equal to the absolute deviation. But it's pretty close to that same idea. So we generally think about it in those terms. The only problem is this is like we have a summation symbol inside a radical, and we're summing over the square of deviations. So there's like a lot of like mathematical notation going on. That's the one downside. Everything else about this is very nice. And we can just easily calculate this in Python. So just like we had with means, we've done this already, but data in Python has a standard deviation built in. So we can just find the standard deviation of any data set. Okay, so in this case, as we sort of visually confirmed before, the standard deviation of group A is much larger than the standard deviation of group B, and in fact, it's almost double. Okay, so we're talking about mathematical definitions right after a mini exam. Good time to take a nap. The reason we're talking about this is because it gives us the vocabulary to talk about one of the biggest ideas we have. I think it's really no understatement to say this is the thing we're about to talk about is one of the big ideas in science. The main idea starts something like this. We have a sample, and what we've done here is sample between two different groups. So these are two different counties, and we can pretend these are two different counties in Pennsylvania. And what I'm doing is just going out, taking a survey of 50 people in two different counties, and then measuring their sleep, and then just plotting the distributions of the two groups. This is the question we've been asking. This is our old question, which is related to summarizing data sets, which is which sample sleeps longer, right? And what we do is we just look at the data and then we compare the averages. So on average, we found group B sleeps just a tiny bit longer than group A. This is our old question. Our new question is going to be, it's going to read very similarly, but be a fundamentally different question, which is this: which county sleeps longer? So this is not a question about the data we just collected. It's not a question of the 50 people in the two counties. This is a question about, does Allegheny County sleep longer than Butler County? Which is a question not about just what we observed in our sample today, but also a question about potentially tomorrow too, and like 10 years ago. This is a question about something that is not in our data set. And whenever I ask scientific questions, it's more like the second question than the first. Right? We care about what's in the sample, but primarily we care about what's in the sample because it informs our understanding of the population. Like 50 people in both groups, who cares? It's about the population. And so when we use a sample to make a claim about a population, that's a careful process, and that's one we're going to explore. Okay, so essentially, what's the main distinction between samples and populations? I made this nice figure. I made this in Python. I think it looks pretty. Essentially, what we're doing is we have a bunch of people or a bunch of potential observations in our population, and no matter how much we observe, how large our sample size is, how large our data set is. We will never observe everything in the population. What we observe is the sample. So in the example I gave you before with sleep times in 2 different counties, we observed 50 observations, which is our sample from the larger population. The population, we don't know the average, we don't know the spread, but we do know the sample size in the sample, and we do know the X bar, and we do know the sample, the standard deviation in the population, in the sample. In our data set, we can see all of these statistics. What we can't see are the population mean, so our mu, population mean, and then we can't observe the population standard deviation. So how spread out is the population? We will never see it directly. This presents a real challenge. So how do we make claims about the population when all we see is this one single draw from the population? Do y'all know how we do it? Like, if you were starting with a data set and trying to make claims about a population, I want you to think about the process you would go through to try to make these kinds of inferences. We're gonna do this from scratch. We're gonna think about all the nuances and develop this machinery. So this is, we observe samples. Samples are often just called data. But the thing we study is not the data, it's the population. Okay, I've said this 14 different ways, 14 times. There are lots of ways to think about what we're doing, but this is the fundamental idea. We have to go from data, which is our sample, to making claims about the population. That's the main thing. If we can't do that, I think we're at a major disadvantage. That's the thing we do in science. We make claims about the population. So just to make this distinction even clearer, the data is 50 individuals, which happen to be samples from both counties. The population is all people who ever lived in these counties, or all people who could have lived in these counties. That's the population. It's this large thing. It doesn't even, the population of a county, we think of as the people who live there now. But as statisticians, we think about everyone who lives there now and everyone who could have lived there now, but don't. It's an abstract idea that we cannot and will never measure. It's theoretical, and this is the fundamental tension. We observe the data drawn from the population, but it's not the population itself. And it's that thing that we can't observe that we're trying to study. Like gravitation. That's a thing we can measure repeatedly, but we will never see it directly. Okay, so what is data? I think you were just describing this very well at the beginning of class. You're saying a record of observations. What we're doing by collecting data is repeatedly drawing from a random variable. We're going to define random variables here in a second. But a random variable is a process about a population. So it's a function that we can essentially just draw from. So the metaphor I'm going to use is something like a deck of cards. What we call the probability mass or density function, depending on whether it's discrete or continuous, we can just call it a probability function, is a function that assigns probabilities to every possible state. So essentially it's the probability for each card. So if we have a deck, we're assigning a probability to drawing each one of the cards randomly. So in a complete deck, it's 1/52. And then the observation is just the realization of that process. So once we draw the card, it's just a record of what the card was. So we draw the card, and then we write down what card we drew. And then a sample is just, we've done this many, many times. So this is what data is. We have a probability density function behind the scenes telling us probabilities over every possible state, and then we're just repeatedly drawing from that underlying probability density function. This is data, And what we're trying to do is make claims about the random variable, which we do not see. Okay, so just to give you a picture of this, I like pictures, and so here we have two probability distributions. So this is county A and then county B, each with a distribution, and each with a population statistics. So this is the average for both, and then the distribution for both. And then these are our samples. So this is just, a histogram of both types. So I've said this a million different ways, but data is a sample drawn from a random variable. And we have lots and lots of different kinds of random variables. We don't just have just the normal distribution, like we'll talk a lot about, or a uniform distribution. We have lots and lots of them. These are 6 different examples. So this is a normal. We'll spend a lot of time with this. We have a uniform distribution, which just assigns equal weight to everything in the thing. So a deck of cards is a uniform distribution over every possible card type. How many of you have seen an exponential distribution? Okay, yeah, maybe a few. That may come from your statistics class. What about a chi-square? This one is often used. We have binomial, which is another one, and then Poisson. This is not poisonous, thankfully. We can use it without fear. Thank you. I will not be here all day. I'm going home. So these are just some of the ways we visualize probability functions. These are things we will not observe. So we're going to do a couple of little exercises here just to get familiar with distributions and how we can work with them. So I know I gave you a mini exam, but I'm still going to ask for an exercise. We have 3 questions. We'll see if we get through all of them today. So here I'm giving you exactly everything we know about the distribution of County A's sleep time. So if we know the distribution, we can make many, many claims about it. So here I'm telling you everything there is to know about the population. In practice, this will never be true. You will never see this. You'll never see the distribution of the probability distribution for the population. But for now, we're going to pretend like we do. And then next class, we'll take this away. All right, so here's the thing. Our data, xi, is distributed normally, so this is a normal distribution, with a center of 7.2, and then a standard deviation of 1.5. Now, we're going to hop over. I know, I'm asking you to do some work right after the mini exam. I know what I'm asking. We're going to do just 3 quick little questions. For almost everyone, this will feel like review. Yeah.
It's saying notebook not found for exercise.
Okay. Hold on a second. It's Zach's saying this is a sign. Authorize with GitHub. Nope. Okay, so we're not going to do this today. I think it is a sign. I checked this right before class, I promise. So we're going to do this at the beginning of class next time. Let me show you some of the pictures we would have talked through, because this is instructive. But this will not be. I'm going to change the due date to be later. Crying emoji. All right. So what we would have done is ask a couple of questions. So what's the proportion of the population sleeping less than 5 hours? The way we answer this, and I'm giving you the answers today, but we're going to do this together at the beginning of class next time. The way we answer this is we can think of a normal distribution behind the scenes. And then we just ask, what's the area under the curve below some number? So what's the proportion of the population that sleeps less than 5 hours? Well, we look at 5, and then we find the area under the curve under 5. And that gives us a number. This is really hard to do without a calculator. Some of you have asked or answered these kinds of questions using the normal distribution. You can there are ways of doing this, but thankfully we have a very functional calculator at our disposal, which we call Python. And we can just ask it directly. So this is just some code to answer how to do this. We want to find the CDF, which is what we call the cumulative density function, which just tells us the probability under the curve up to some number. We want to find the area under the curve up to 5. And then we tell it where to center the normal distribution. So we center it on the average of 7.2. And then we want the spread to follow sigma. So we want it to be as spread out as 1.5. And when we print this out, it gives us a number. I'm not going to tell you what that number is yet. We're going to do this in code next time. But that's how we think about the problem. If I were to ask you this question, I want you to turn to someone next to you. We're not actually doing this mathematically, but turn to someone next to you and tell them sort of generally how you would think about answering this using a CDF or the distribution itself. What's the picture you would have in your head? We'll take maybe a minute here.
Just look for the section that's
Okay, someone want to tell me how you would think about this problem? Yeah.
You could see how many standard deviations 9 hours is away from the mean of 7.2, and that should give you the rough percentage.
Okay, nice. So yeah, in our stats classes, we talk a lot about these known probabilities, right? We know some general things about the area up to a certain number of standard deviations. If 9 happened to be one of them, then we could just make a claim using these known distribution, or these known sort of cutoffs on the normal distribution. I'm sorry, is it Brad?
Yeah.
Brad. Yeah, so this is our standard approach. And then we can look in the back of our textbook at the summary, the probabilities given to us about normal distributions and z-scores and all of this. And then you all have those in your stats textbook. There's huge lists of numbers. So you could do it that way. But the general approach here is just to find the area under the curve that's greater than 9. That's the picture you have in your head. Area under the curve greater than 9. And then we try to find everything above this. It turns out there's a very nice way to do this in Python. We no longer need that big list of numbers in the back of our textbook. We can just go to code to do it for us. And the way I think about this is I want the CDF up to 9 to get the area under the curve that's not 9. And then I'm going to subtract that number from 1, which is the entire area under the normal distribution. So I'm going to say I'm going to take 1 and then subtract off the CDF just like before, except we're swapping 5 for 9. So the area in white here, I'm going to subtract off from 1, and that leaves me just with this red area. Okay. One last question, and then I'm going to send you out the door early today. How much sleep does the middle 92% of the population get? So the way I would start to solve this problem is by first either on a piece of paper or mentally drawing a picture of this distribution. Like, we have a normal distribution, we know it's normal. How do we just visually set up the graph for the answer to this question? That's the place to start. Take maybe 2 minutes here. This one's a little trickier. Okay, someone want to paint a visual picture for me? What are we graphing when we graph the answer to this question? Pete.
Take out the bottom 4% and the top 4%, just to get evenly on both sides to get the middle 90%.
Okay, so Pete's recognizing we have 92% in the middle, so that leaves us with 8% total on either end. So if we split 8% evenly between both ends, we get 4% on both ends. So the picture is essentially just the middle portion with 4% on either side. So maybe something that looks generally like this. Without knowing exactly what the numbers are, it would look like this. Yeah. How many of you had a figure that looked something like this? Hands up. Okay. And then the way we would find the answer to this question using code is just to find, first off, how much is in the one tail. So how much is below this value. So the CDF up to this point. And then we want to find the 1 minus the CDF that includes 4% on the upper side. So we want to find the number that corresponds to the lower 4%, and then the number that corresponds with the upper 4%. The code is slightly different, but we have code that answers this question exactly for us. This is what's called a PPF. This is not your production possibility frontier that you know and love from your intro theory classes. This is just a way of getting the values, the bounds, using code. So this is getting the lower 4%, so it tells us what point on the distribution gives us exactly 4% less than it. So the fourth percentile. And then here we have the 96th percentile. So so this point. And then we just tell it, the location and then the scale for the normal distribution. Okay, so I'm hoping for nearly everyone in this room, this is good news. This is like, we no longer have to use that table at the back of the textbook. We can just ask code to do it precisely how we want it. Python has this like huge library of these numbers, and all we're doing is just asking for the right one. We're going to spend some more time doing this next time, but just to wrap up what we've done today, well, first off, we took a mini exam, but the main idea with what we're doing is to ask the questions about the distributions when we don't know the distribution itself. What we just walked through was a case when we did. And there's a reason we like thinking about distributions like this. There will be a kind of distribution that we will know. But most of the time, we will not know the population distribution. What we do see is a sample size. we see a sample mean, and then we see a sample standard deviation. So the things we can measure in our data. What we don't know, and what we generally have questions about, is a population mean. So what's the average sleep time in the county? What's the spread of the sleep time in a county? And we don't know the population distribution itself. We don't know if it's normal. We don't know if it's like gamma. There are lots of different distributions. It could be. Could even be like weirder ones. We don't know what it is. So what we're doing in part 3, 4, and 5 is talking about how we go from not knowing and only observing our sample to knowing the population. These are two entirely separate ideas, right? The sample statistics and the population statistics. And what we're doing is trying to use one to tell us something about the other. Okay. This is where we're going. Next class, we're going to talk about the central limit theorem, which is a truly magical idea. Like, if there is magic in the world, it's in part 3.2. And then from there, we're going to talk about the rest of how we start building up these core ideas and how we build statistical models. Some of this will feel very familiar. I think a lot of the ways we talk about it in this class are just slightly adjacent to the ways you've seen it before, because we're building up a much larger statistical model. I'll see you all next time. Congrats. Go treat yourself like Pavlov, right? Give yourself a little treat when you do a hard thing.
Thank you.
Evan, right?
Yeah. Taylor, right?
I just give myself quizzes sometimes.
It's good. I've never been phenomenal with names. So
Okay.
I've been trying to practice when people tell me names, I'm name.
Yes. Well, good job.
I have a quick question.
Yeah.